Welcome to the Problemers channel, season 2, episode 52, the episode which I titled of Mice and Wine and Coins, because with these characters on the stage, we will solve an initial problem that will unlock our initial study of a very powerful but admittedly quite challenging problem-solving approach to which I refer as mathematical equivalence. Before we do that, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Welcome to our channel, and thank you for subscribing to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from working with the material that we present on this channel is to go to the homepage of this channel, and in the channel's trailer section, find the episode titled The Problemers Channel How To. Watch that episode in its entirety. We suggest that you follow all the instructions that we give in that episode. If you have any questions, then by all means do ask. I will make sure that I'll find the time to answer all your questions. But in that episode, we explain and motivate everything that we do on this channel. In the mathematical problem S2E52, we are asked to essentially solve two problems and then decide whether the solution of one such problem can be mechanically converted or translated into a correct solution of the other problem. That is, the problems themselves are not very difficult. They're actually more than straightforward. Each one by now we already know is solved within minutes. In the first problem, we have two lab mice. We have 9 visually indistinguishable bottles of wine. We know with absolute certainty that only one bottle contains the wine that's poisoned, and we're asked to find a testing scheme using which, with absolute certainty, it can be determined which of these 9 visually indistinguishable bottles contains the wine that is poisoned, using two tests or two tastings. The definition of one tasting is the following: mix the wine from all the bottles that you have in any which way to your heart's content, feed one such cocktail to one mouse, maybe feed it to the other. That is one tasting, one test. Determine with absolute certainty, with two tests, two lab mice, which bottle contains poisoned wine, if again poison acts instantaneously or very, very quickly. In the second problem, this is a 9-coin problem. This is a classical one. 9 visually indistinguishable coins. One is known to be fake. With absolute certainty, the quality of that fakeness is known. Let's say it's fake and heavy. We're given one properly functioning, not rusty or anything, properly functioning set of pen scales, 2 pen scales, everything works fine, and we're asked to find the testing scheme, according to which we can find an absolute the fake coin with absolute certainty, and I think in the smallest number of weighings. And then I forgot to say over here last time, 2 weighings. 2 weighings. So find the testing scheme, which in 2 weighings determines with absolute certainty the identity of the fake and heavy coin. Now that we have 2 solutions, the actual challenge in this problem is the following: can one correct solution of the correct solution of one of these problems be mechanically converted or translated into a correct solution of the other such problem? Do not worry if you were not able to solve this problem completely correctly and on your own. This problem is actually quite difficult, but the reasoning behind why the answer to the third question in this problem is what it is unlocks our initial study of a very powerful, even though admittedly quite challenging, problem-solving approach to which I refer as mathematical equivalence. Across the 2 problems that we will consider in this episode, we will solve the first problem, the 9-bottle problem, first, and we will present 2 essentially equivalent solutions of that problem: a geometric solution and an equivalent algebraic solution. A geometric solution of the 9-bottle problem is very visual, and students usually have no problems comprehending such visual solutions. And on the other hand, algebraic solutions tend to be much more abstract, and sometimes students have problems comprehending more abstract solutions. That is why first we will present a geometric solution of the 9-bottle problem, and after that, once the essence of a geometric solution of the 9-bottle problem is understood, understanding the essence of the equivalent algebraic solution will be that much more straightforward. To that end, it so happens that the basis or the foundation for both a geometric and an algebraic solution of the 9-bottle problem is a square. Consequently, first take all 9 bottles given in the first problem and arrange them in a 3 by 3 square as shown on the left side of your screen. In order to refer to the mice in this problem in a way, I will name one of these mice as a horizontal mouse, and I'll designate it with the letters M, H. H will stand for horizontal mouse. And the other mouse I will name as vertical, and I will refer to that mouse as M, uppercase M. V for vertical mouse. You can name your mice in any which way that you like. You can name them Uncle Bob and Aunt Sally. And why I have named my lab mice as horizontal and vertical will become evident in a few seconds. Recall that in a 9-bottle problem, we're allowed to carry out no more than 2 tastings, and according to our definition, one tasting is an act of mixing wine from any number of bottles that we wish and feeding that cocktail to one or more mice. As such, for the tasting number 1, for the first tasting, as I depicted over here on the left hand of your screen, T1 stands for tasting 1. The idea is to construct 2 cocktails which take the wine from the total of 5 bottles under the condition that both cocktails share the wine from precisely 1 bottle. Geometrically, that means at first that we take the wine from the bottles that sit on the blue line, for example, shown over here and over here. And once we think about it, once the essence of a geometric solution of the 9-bottle problem is understood, we will quickly realize that we have many choices. There is no fixed or there is no single unique choice. What that means is that for the tasting number 1, the 2 cocktails can be mixed from the bottles that sit on the blue lines shown over here in the cross formation, or shown over here in the angular formation, or shown over here in the diagonal formation, if you will. The formation from which the 2 cocktails are formed can be can also look like this, or like this, or like this. And once again, in real time, at first it may not be that much evident, but when I played with this problem, eventually I realized, the act of putting the bottles, the wine from which is mixed into 2 different cocktails on a straight line, as shown in 6 formations over here. And this is just some formations. These are not by all means all the formations, and maybe it's a good idea for you guys to experiment with them. But then I realized, the bottles, the wine from which is taken in order to mix the 2 cocktails, do not really have to sit on a straight line. They can form angular shapes like this over here. For example, on the bottom, in a slightly larger 3 by 3 square, I showed you the green angular formation for 3 bottles that goes into 1 cocktail. and the red angular formation of another 3 bottles that go, the wine from which goes into making the second cocktail. But essentially, and the fundamental feature of all these choices is what? Is the fact that no matter how we pick the needed bottles in order to make 2 different cocktails that we will feed to 2 different mice, these choices must intersect, if you will, geometrically. And as we shall see in the algebraic solution when we frame our discussion in terms of sets, so there will be intersection of sets, but in the language of geometry, the 2 formations must intersect at precisely 1 bottle, as shown over here. This is the common bottle, this is the common bottle, this is the common bottle for this choice, this bottle is common for this choice, this one, and in the angular formation it is evidently this one. And why that works, again, be a little bit patient. In a few seconds you will realize why this flexibility is available to us. And again, purely for the sake of storytelling convenience, I will go with this choice, and at, I'm not sure how deep or mathematically hefty that choice is, there is some nicety, there is some elegance built into this choice. And for those of you guys who are quick to think on your feet, think as a short quiz, why did I choose this particular formation? Again, the answer is coming in a few seconds. But for the tasting number 1, for the cocktail number 1, we will take the wine from the 3 top horizontal bottles, and that is why I named that lab mouse horizontal. And for the second cocktail, we will take the wine from the 3 leftmost vertical bottles shown over here, like so. And we will feed this cocktail to the vertical mouse. One more time. For tasting number 1, we will mix the cocktail number 1, which is a collection of wine taken from the top 3 horizontal bottles, connected here with the blue line, and we give that cocktail to the horizontal mouse. And for the cocktail number 2, we will mix the wine taken from the 3 leftmost vertical bottles shown over here with the blue line through them, and we will feed this cocktail to the vertical mouse. And now we want to see what are the possible outcomes of the tasting number 1. If you were not able to solve this problem correctly, completely, and on your own, use this as an opportunity to practice mathematics correctly. We suggest that you do not listen to our presentation, but put this video on pause and try to think on your own. As per the tasting 1, as we designed over here, and the design is shown on the left side of your screen, how many possible outcomes of that tasting will be, and what are they? Meanwhile, we, as Isaac Newton used to say, upon thinking about it, realize that the tasting number 1, as it was designed by us in the previous segment, can have 4 and only 4 outcomes, and these outcomes are complete. In other words, there are no other outcomes. And these 4 outcomes are the following. The first possible outcome is when both mice die. The second outcome is possible when only the horizontal mouse dies, but the vertical mouse lives. The third possible outcome is when only the vertical mouse dies, but the horizontal mouse lives. And the fourth and the final outcome is when both mice live. If as the result of the tasting number 1, T1, whose design is shown on the left side of your screen, it so happened that both mice died. In other words, we witnessed the outcome number 1 shown over here, both mice die. Then what does that mean? That can mean only one thing. It means that both mice imbibed a wine that was poisoned. But because we designed our tasting number 1 precisely in a way that only one bottle, or the wine from only one bottle, was shared across 2 cocktails, and that is this bottle over here. In this case, it happens to be the upper left, the bottle in the upper left corner. That means that the poisoned wine could come only from the bottle that was shared across the 2 cocktails. That means that, again, in the first outcome, when both mice die, we clear the remaining 8 bottles shown over here at the bottom from any suspicion with absolute certainty. It is absolutely safe, and we're absolutely certain that it is safe to drink wine from the remaining 8 bottles. And with absolute certainty, we know that the poisoned wine came from the shared bottle, or in this case, it will be the bottle that sits in the upper left corner, and we can mark it, for example, with red like this. This is the poison bottle. We know that with absolute certainty, and in some way that process evidently terminates our geometric algorithm. If as the result of the tasting number 1, whose design is shown over here on the left side of your screen, it so happened that only the horizontal mouse died, but the vertical mouse did live to tell the tale, what does that mean? That can mean only one thing. First, it means that there was no poison in the wine taken from the 3 leftmost vertical bottles shown over here. In this case, 9 minus 2, 7, we cleared with absolute certainty the 7 bottles shown over here. This bottle and the 6 bottles below are cleared of any suspicion with absolute certainty. And by the same token, that means that since only the horizontal mouse died, but the vertical mouse did not, and it lived to tell the tale, it means that with absolute certainty, we place the 2 horizontal bottles shown over here. I will circle them in red. We place these 2 bottles under suspicion, and that means that we know with absolute certainty that the wine that was poisoned and the one that killed the horizontal mouse came from one of these 2 bottles. And thinking on our feet further, we also understand that once we analyze that outcome, we know that we have only 1 tasting left and 1 surviving mouse, the vertical mouse, in order to determine the bottle from which the poisoned wine came with absolute certainty. The third outcome of the tasting number 1 is actually symmetrical with respect to the second outcome of the tasting number 1. That is, if as a result of the tasting number 1, whose design is shown on the left side of your screen, it so happened that only the vertical mouse died, but the horizontal mouse did not die and lived to tell the tale, that can mean only one thing. First, it means that there was no poison in the topmost 3 horizontal bottles over here. That is why the horizontal mouse survived. And that means that with absolute certainty we can clear of any suspicion the remaining, shown over here, 7 bottles of wine. The 6 shown over here in a nice column and the 1 shown over here. Secondly, it means that with absolute certainty, precisely because only the vertical mouse died and the horizontal did not, the wine that was poisoned and the one that killed the vertical mouse came from these two bottles. I will circle them in red also over here. And again, we understand that in the next segments, when we will begin analyzing the construction or the algorithm for the design of the tasting number two, we will have what? We will have one surviving mouse horizontal in this case and one tasting left in order to discriminate with absolute certainty between which one of these two bottles contains the wine that is poisoned. In the fourth and the final outcome, if it so happened that as a result of the tasting number one, whose design is shown on the left side of your screen, neither of the mice died and both of the mice survived to tell the tale, then that means only one thing. First, it means that there was no poison in the wine that was used for the construction of the two cocktails that were given to the horizontal and to the vertical mouse. And that means that with absolute certainty we clear the 5 bottles shown over here, the wine from which was used for the construction, for the mixing of the cocktails. And that implies what? That implies that with absolute certainty we place the suspicion on the only 4, 9 minus 5 is 4, on the only 4 remaining bottles. These bottles are under suspicion. I will circle these bottles in red, shown over here, and by now our viewers can validate their ideas against mine. In some sense, the the geometric sugar that we witness right now explains why I went for this an original geometric design of the geometric solution of this problem, because now once we begin analyzing the design of the second tasting, it becomes evident that we have what? 9 is 3 squared is a perfect square. 9 minus 5 is 4. 4 is a perfect square. So in this case, what do we have? We have a smaller version of the original larger problem. So in some sense, we already see where this is going. And in this case, we will design exactly the same, or recursively, we will design exactly the same tasting, the mix of wines for the cocktail number one and number two, in a way that we designed the cocktails for the tasting number one. I already explained that in the first outcome of the first tasting, our geometric algorithm terminates. There is nothing to do because we know with absolute certainty the bottle that contains the poisoned wine, and that is the bottle that is the intersection of the 5 bottles that were used for the mixing of the two cocktails that were given to the horizontal and to the vertical mouse. In the second outcome, when only the horizontal mouse dies and the vertical mouse lives to tell the tale, then we already explained in the previous segment that under suspicion, with absolute certainty, we have these two horizontal, let's say logically speaking, horizontal bottles. And that means that the poisoned wine is contained by one of these two bottles. And in order to discriminate between these two bottles, we have precisely one tasting left and we have one surviving mouse. In this case, it is the vertical mouse MV. Now, you do not really have to be an Einstein or Leonard Euler to figure out what is going on. Street smarts, basic situational awareness is needed in order to design the second tasting for the case number two, and that is what? We take the wine from only one bottle. Which one, it doesn't really matter. We call that wine a cocktail, and we basically give the wine from one of these two bottles, from one of the two horizontal bottles circled in red over here, we give it to the surviving mouse MV and we observe the result. And how many outcomes in this case are possible? Only two outcomes. The surviving mouse MV either dies or it survives. If the mouse, let's say in this case the vertical mouse, dies after tasting the wine from, let's say, this bottle over here, evidently because the wine for this cocktail came only from this bottle, that means with absolute certainty that the other bottle, this bottle, is cleared, and we cleared all eight bottles this way. And with absolute certainty, we know that the bottle that contains the poison one is this one, the one that was given to the vertical mouse. And conversely, if after taking wine from this here bottle, the vertical mouse does survive, that means that with absolute certainty, on the one hand, we clear that bottle, the wine from that bottle, from any suspicion, and thus we clear all 8 bottles. And that means that the poison that was in the wine that did not kill the mouse MV came from this bottle over here. And again, it should be understood that we can give the wine for the second tasting, for the tasting number 2. Let's mark it over here for the tasting number 2. For the tasting number 2, we can give the wine from the other bottle to the surviving mouse MV and observe the same result. If the mouse MV dies after imbibing the wine from this bottle, then that bottle is poisoned with absolute certainty and we clear the other one. And conversely, if imbibing the wine from this here bottle, the mouse MV does not die, then with absolute certainty, this bottle, the remaining horizontal bottle over here, is the one that contains poison with absolute certainty. The design of the tasting number 2 in the third outcome of the first tasting is actually absolutely symmetrical with respect to the design of the tasting number 2 for the second outcome of the first tasting. That is, if as a result of the tasting number 1 it so happened that only the vertical mouse dies but the horizontal mouse does not die and lives to tell the tale, then in this case, as we explained in the previous segment, with absolute certainty, the 7 bottles shown over here, this 6 and this 1, are cleared, and with absolute certainty, these 2 leftmost bottom vertical, so to speak, logically vertical bottles under suspicion. That means that the bottle that is poisoned is one of these 2, and we have precisely 1 tasting and 1 surviving mouse MH, the horizontal mouse, in order to discriminate between these 2 bottles. And from the standpoint of information theory, we have how many outcomes for this tasting? Well, we have only 1 mouse, so we design our tasting in such a way that either the horizontal mouse dies or the horizontal mouse does not die and survives to tell the tale. 2 outcomes, 2 bits of information, and we can map these 2 bits of information to 2 objects over here if we design our test correspondingly. Again, you do not have to be Euler, you do not have to be Carl Gauss to design this step. Basic street smarts, basic situational awareness, common sense tells us that in order to locate or identify the poison bottle with absolute certainty, all we have to do is take the wine from only 1 bottle and feed it to the surviving mouse. Let's say we take the wine from the top bottommost leftmost vertical bottle over here and give it to the horizontal mouse. If that mouse dies, then we know with absolute certainty that this is the poisoned bottle and we clear the other one from suspicion. And conversely, if the horizontal mouse, after imbibing the wine from this bottle, does not die, then that means with absolute certainty that this, the bottom one bottle, is poisoned with absolute certainty. We can also design our tasting number 2 in another way. Feed the wine to the surviving horizontal mouse from the bottom bottle over here, from this bottle, and observe the result of the tasting number 2. If the horizontal mouse does die, then with absolute certainty this is the poison bottle that just killed the horizontal mouse. And if the horizontal mouse does not die, then we clear that bottom bottle from suspicion with absolute certainty. And with absolute certainty, we know that the poison bottle is this one right here. And now we only have to see what is going on, how we design the second tasting for the fourth outcome of the tasting number 1. The geometric sugar, if you will, of my original choice for the geometric, for a geometric solution of the 9-bottle problem shown over here will become evident right now, because in the fourth and final outcome of the tasting number 1, for the tasting number 2, we basically have a smaller version of the original problem. The original problem was a 3 by 3 square, which is 9 bottles. Now we have a 2 by 2 square, which is 4 bottles again. If you recall the options that I gave you guys on the right side of the screen a few segments ago, all these various ways to put the wine into 2 cocktails based on the straight lines that cross the 5 bottles in such a way that these 2 straight lines intersected precisely 1 bottle, also lead to the same basically residue, if you will, 4 bottles, except that these 4 bottles are sprinkled in some funny way. But here they're sprinkled quite nicely. They're tightly grouped, and now the recursive application of the original algorithm to the fourth outcome becomes evident. That is, how many surviving mice do we have in this case? Well, we have precisely 2. Remember, both mice survived to tell the tale. We have the horizontal mouse alive and kicking, we have the vertical mouse alive and kicking, and we have what? We have only 1 tasting. And here we have 4 distinct bottles. How many units of information? Well, 4 units of information. Consequently, we need to design our tasting. It's a precious tasting, if you will, because it's the only one. We cannot mess things up, so we have to design it in such a way that we produce at least 4 outcomes. So then from the information theory standpoint, we have at least 4 units of information produced by the test, and we need to map these 4 units of information to another 4 units of information that we associate with our bottles. How do we do that? Well, do exactly the same thing. For the cocktail number 1 over here, we mix the wine from these 2 logically horizontal bottles, and we give them to the mouse MH, the horizontal mouse. And for the second cocktail, we mix the wine from the bottles shown over here, logically vertical, 2 leftmost vertical, 2 topmost horizontal to the horizontal mouse, and 2 leftmost vertical to the vertical mouse. This is it, game over. Exactly the same approach or idea that we use for the tasting number 1 in our setup, in the original setup. And what are the outcomes? Well, again, precisely the same 4 outcomes that I cleverly kept on the board for you guys. In this case, precisely because we have 1 intersection bottle, and this is the situation that is similar with the previous design of our 2 cocktails. With these 2 cocktails, we can have the following 4 outcomes. Both mice die. In this case, the horizontal and the vertical mouse die at the same time after they imbibe our cocktail. Only the horizontal mouse dies, but the vertical mouse survives to tell the tale. The third outcome is only the vertical mouse dies and the horizontal mouse survives to tell the tale. And the fourth case is when both mice survive and neither one dies. 4 outcomes, 4 units of information mapped to 4 distinct bottles where there is a hope for absolute certainty, and we see what in the first case, when both mice die, then what does that mean? That means that they imbibe the poisoned wine at the same time. And which bottle did the poisoned one could come from into for both cocktails? The cocktail that was given to the horizontal mouse and the cocktail that was given to the vertical mouse. Well, this bottle right here. So in this case, in this outcome, we know with absolute certainty that this is the bottle that contained the poison one, again with absolute certainty. In the second outcome, when only the horizontal mouse dies, but the vertical mouse does not die, that means what? It means that there was no poison in the shared bottle, the wine from which came into both cocktails, and that is why the vertical mouse lived to tell the tale. There is no wine in this bottle, there is no wine in this bottle, but this leaves what, in some sense, this is a tiny manifestation of eliminate and conquer. Once everything that is impossible has been eliminated, whatever remains, no matter how improbable, is the truth. In this case, bam, this bottle right here, this bottle right here is when the horizontal mouse dies. This bottle right here with absolute certainty is the poisoned one. In the third outcome, when only the vertical mouse dies but the horizontal mouse does not die, what does that mean? That means that there was no wine in the top horizontal bottles, no poison here, no poison over here. The poison was, again, by eliminate and conquer, miniature manifestation or miniature incarnation of eliminate and conquer. The poison came only from the bottle shown over here at the bottom, because the vertical mouse did die and the horizontal mouse did not die. So we know with absolute certainty we clear all the other 8 bottles of any suspicion, and that means in this case that this here bottle was the poisoned one with absolute certainty. So we map this case to this one, and when this case, in the case when the vertical mouse dies, and now we have only one case left. In the fourth and the final outcome of the tasting number two, whose design is shown over here, the cocktail from the 2 leftmost vertical bottles go into the cocktail that is given to the vertical mouse. The wine from the 2 topmost horizontal bottles go into the cocktail that's given to the horizontal mouse. Both of these mice did make it. None of them is dead. And what does that mean? Again, in a way, tiny milli, micro, or nano manifestation of the eliminate and conquer. Only 4 choices were given to us. 3 have been eliminated. What's the only choice, no matter how improbable? Yes, in this case, with absolute certainty, this is the bottle that contains the wine that is poisoned. We know that for sure. We connect this to this case over here, and now that you guys understand how the essence of this geometric solution of the 9-bottle problem, I recommend that you go back and play with the angular formations that I promised to you guys that You can pick the bottles for the cocktail number 1 and the cocktail number 2 for the first tasting in a way that is not necessarily straight line based, but based on angular formations, and try to see what does that mean. Meanwhile, we will move on using and keeping this geometric solution of the 9-bottle problem in the background as a backdrop. We will design the corresponding algebraic solution of the 9-bottle problem. For an algebraic solution of the 9-bottle problem, we will still use the 3 by 3 square formation that we used for a geometric solution of the 9-bottle problem as our foundation. And by doing so, we will embed the algebraic solution of the 9-bottle problem into the base 3, because it so happens that 3 distinct symbols completely describe the material that we're given in this problem, namely the 9 bottles. And remember that embedding this or that informationally flavored problem into the appropriate numeric base 2, base 3, base 4, base 5, and so on, sometimes give us a competitive advantage, because if we can control the variance of the alphabet across the corresponding bit positions, then sometimes that control allows us again to gain a competitive advantage, because by varying that bits in all the possible ways, we produce a sort of optimality where we cannot miss any possible configuration, and by enumerating all the possible configurations, we can sometimes draw an appropriate and victorious conclusion. And in this case, we embed our algebraic solution of the 9-bottle problem into base 3 as follows. Using the 2-bit words x, y, we assign unique tertiary names or base 3 names to all 9 bottles in such a way that, again, you don't have to do it this way. I just did it this way for demonstration purposes. The leftmost, or logically the first bit in our 2-bit word, will represent the row number in our naming, and the second or the last bit in our 2-bit tertiary word will represent the column number. And by using this notation shown over here, we assign the unique base 3 names to all our bottles, and in a way this is a mechanical algorithm, if you will, to enumerate all possible base k numbers without missing any ones. For your convenience, guys, I showed the letters or the alphabet, the base 3 alphabet, in 3 distinct colors. I picked the numbers 0, 1, and 2, but we remember that for representing numbers in certain base, the alphabet doesn't really matter as long as the pictures are distinct. We're in. Here the pictures are 0 shown in red, 1 shown in green, 2 shown in blue, and voila, here we go. 0 row over here, the first or the leftmost bit is 0, 0, 0. The row number 1 shown in green over here, the leftmost bit is 1, 1, 1. And the bottom row is number 2, the leftmost bit over here shown in blue, 2, 2, and 2. And in the same way, we name the columns as well. The column shown over here is 0, 0, 0 in red. This is the column number 1. It is shown over here in green, 1, 1, 1. And lastly, the last vertical column is number 2, shown here in blue, 2, 2, and 2. And it is evident that this is a mechanical way. In a way, it's a matrix representation, if you will. We understand that for the first position, how many different choices do we have? Well, we have 3 distinct choices for the number of unique symbols in base 3. And regardless of the choice for the letter from the alphabet of base 3 we pick, how many choices do we have for the second positions to fill in? 3 as well. Yes, and by the multiplication counting principle, we get 3 squared, or precisely 9 choices. So technically what these names are? Technically these names are finite linear permutations of 3 distinct items over two positions with repetitions. As you can see, repetitions are allowed across the main diagonal, if you will. 0, 0, 1, 1, 2, 2 are repetitions. And once that is understood, the assignment of the unique base 3 names to all 9 bottles. Once that is understood, the design of the tasting number 1 and tasting number 2 should be straightforward. Keep in mind the geometric solution that I guys showed you and that we now understand. And we basically, what we do now is we lay our geometric solution on top of this algebraic one, see what's going on, take a picture, throw out the geometry, and leave only the algebra of these tastings, which is once it is understood how we design the unique names in base 3 for all the given 9 bottles shown on the left side of your screen, we design the cocktails for the tasting number 1 as follows. Just like in the geometric solution of the 9 bottle problem that we presented previously, in the algebraic solution of the problem, we designed 2 different cocktails. The cocktail named H, for example, which we feed to the horizontal mouse MH, and the cocktail named V, which we will feed to the vertical mouse MV. Into the cocktail named H, we put the wine that is taken from all the bottles that have the symbol 0 in their first or leftmost bit of their base 3 or tertiary names. That means that the wine that goes into the cocktail named H is taken from the bottles whose tertiary names are 00, 01, 02. Why? Because we have evidently only one row named 0, the top one, and in that row we have how many columns? We have 3 columns. Consequently, the names of the bottles are 00, 01, 02. 0 is the first position in the tertiary name of this bottle. 0 is in the first position of the tertiary name of this bottle. 0 is in the first position of the tertiary name of that bottle. Row, 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 0, 0, 0, 0 row, 0 row, 0 row. I highlighted these rows for you guys over here. And we feed that cocktail to the horizontal mouse MH. The cocktail V we construct as follows. For the cocktail named V, we put the wine from all the bottles that have 0 in the last or in the second bit position of the tertiary names of these bottles. We remember that in our XY notation, the second position corresponds to what? To the column number, and how many rows we have in the column number 0. Evidently 3 rows. Consequently, the names of the bottles, the wine from which goes into the cocktail named V, are as follows: 0, 0, 1, 0, 2, 0. Again, 0 is in the second or the last bit of the tertiary name of these bottles. Column number, column number, column number, 0, 0, 0, highlighted over here, guys, for your convenience, like so. This is as straightforward gets. And now we see, again, if we connect our bottles that go into the wine from which goes into the mix called H with a straight line, we will have our horizontal line. If we connect with one line all the bottles, the wine from which goes into the mix called V, we will get basically our perfect geometric analogy. And here again we see the parallelism between the geometric intersection at a given point and a set theoretic intersection. By definition, an intersection of two sets is another set that contains the elements that belong to both sets. In this case, we have the set which I named also H. It has 3 elements. The set named V has 3 elements, and the set theoretic intersection, we remember it's symmetric. H intersected with V is the same as V intersected with H, and that set contains only one element, and that is the bottle 0, 0. Everything converges nicely, and this is precisely how the tasting number 1 works. And we conduct that tasting, and I will explain how to record the results of that tasting in a few seconds. Once we understand how the mixing of cocktails for the tasting number 1 works, the mixing of cocktails for the tasting number 2 is basically almost a verbatim copy of what we did for the tasting 1. This is tasting number 2, with one change: uniform replacement of 0 as the driving force, if you will, or the driving symbol, with the tertiary symbol 1. That is, for the tasting number 2, shown over here, we also design 2 cocktails. We name one cocktail H. We feed it to the horizontal mouse MH. We designed the second cocktail called V. We feed it to the vertical mouse MV, and into the cocktail named H for the tasting number 2, there goes the wine from all the bottles that have what? Instead of 0, they have 1 in the leftmost or first position of their tertiary names. That means that the bottles, the wine from which is mixed into the cocktail named H, are taken from the first row. Evidently, there is only one row that is named with 1. And how many columns in this row? 3 columns. Consequently, the names of the bottles, the wine from which goes into the mix named H, are 1, 0, 1, 1, and 1, 2. 1, 0, 1, 1, 1, 2. 1 for the row number, 1 for the row number, 1 for the row number, again highlighted here on top for you guys, so you pay attention to the first position, to the tertiary symbol in the first bit or the leftmost bit of the tertiary name of the columns, and into the cocktail named V, there goes the wine from all the bottles that have the same tertiary symbol 1, but where? Not in the first, but in the second or rightmost bit of the tertiary name of all the bottles. And again, because there is only one column named 1, it's this middle column over here. How many rows in that column? 3 rows, consequently 3 names, and these names are 0, 1, 0, 1, 1, 1, this bottle right here, and 2, 1, 2, 1, this bottle right here. Again, the set theoretic intersection of the bottles that belong to the set H and to the set V is shown over here. What is that intersection amounts to? That intersection amounts to the single bottle named 1, 1. The tertiary name of that bottle is 1, 1. Now that you guys see a nice and beautiful picture, I will mess it up a little just to bring home the idea that this here algebraic solution of the 9-bottle problem and the geometric solution of the same problem that we considered a few seconds ago are basically equivalent and constructed one from another. If you hit upon a geometric solution of the 9-bottle problem, then it's a natural step forward into the underlying algebra. And conversely, if you design this solution, the algebraic solution first, stepping back into the geometric interpretation of this algebra is also quite natural. And that goes to one of the running themes that you will see among other things on this channel, is a happy coexistence of algebra and geometry, just like a happy coexistence between physics and mathematics. The one feeds beautiful ideas into the other, and the other feeds beautiful ideas into the one back. So now, once we feed the cocktail named H to the horizontal mouse MH, and once we feed the cocktail named V to the vertical mouse MV, we record the result of the tasting number 2, and we interpret these results as follows. the reason why I mess things up on the left side of your screen over here by drawing the blue lines, two verticals, two horizontals, as you can see over here, is to show you the analogy between an algebraic solution that we're discussing right now and a geometric solution of the same 9-bottle problem that we discussed earlier, and the way we interpret the results of each tasting in this algebraic version of the solution of the 9-bottle problem is as follows. If after the first tasting the horizontal mouse dies, then we record 0 into the leftmost bit of the 2-bit tertiary name of the future poison bottle. And if the vertical mouse dies, shown over here with the cross, then we record 0 into the rightmost or to the second bit of the 2-bit tertiary name of the future poison bottle. If the horizontal mouse does not die, we record nothing in the leftmost bit, and if the vertical mouse does not die, we also do not record anything into the rightmost bit of the tertiary name of the future poison bottle, because the jury is still out. We want to conduct more experiments. Now, if after the test number 2 the horizontal mouse dies, then we record 1 into the leftmost bit of the tertiary name of the future poison bottle, and if the vertical mouse dies, then we record 1, we put down 1 into the rightmost or the last bit position of the tertiary name of the future poison bottle. And to cover the last two cases, if the horizontal mouse does not die by the end of the second tasting number 2, we put down 2 into the leftmost bit of the tertiary name of the poison bottle, and if the vertical mouse does not die after the test number 2 is over, we record 2 into the last or rightmost bit of the tertiary name of the poison bottle. And that recording and that interpretation should be very transparent because of my mess over here that I made of this beautiful matrix, beautiful table. I messed it up precisely to show you guys why we interpret the results of the tasting 1 and tasting 2 in the algebraic version of the solution precisely that way. It should be straightforward, because the reason we write down zeros is because, remember, we put the mix of wines into the cocktail that we gave to the horizontal mouse that have precisely 0 in their leftmost position. That's why left goes into the leftmost position if the horizontal mouse dies. And we put the mix of wines for the second cocktail that we fed to the vertical mouse by taking the bottles with the names that have 0 in the second or rightmost bit. And if this vertical mouse dies, precisely 0 is indication that we have a suspicion. So 0 goes into the rightmost position. It is as straightforward as it gets. It's basically a kindergarten variety. For the second tasting, we replace 0 with 1. Consequently, the same idea is shown over here. We put 1 into the left or 1 into the right position, depending on which mouse dies. And if no mouse dies, we put 2's into corresponding positions. And voila, by the end of this recording, we will have a 2-bit unique tertiary name of the poison bottle. For example, let's conduct this thought experiment. Let's say after the tasting number 1, both the horizontal mouse and the vertical mouse died. We record 0 into the left position, 0 into the right position, 2-bit unique tertiary name, 0, 0. This is our bottle right here, and it sits in the intersection precisely. Let's take the other extreme case. None of the mouse died by the end of the tasting number 2. We put 2 into the left position, we put 2 into the right position. 2, 2 is the name of the poison bottle. Where is it? Bam, it's right here, precisely. You can see over here I overlaid the algebra with the corresponding geometry, and that should be evident. And let's say some other case that we can consider. Let's follow. After the tasting number 1, the horizontal mouse, let's say, survived, it's alive, and the vertical mouse did die, is evident by the cross over here. I crossed it out. And it so happened that after the end of the tasting number 2, let's say the horizontal mouse did survive. What is the name of the poison bottle? Well, we do these things by the book. The vertical mouse died at the end of the test number 1, so we put 0 into the leftmost bit. We put 0 into the leftmost bit. I'm sorry, into the rightmost bit. See, this is 0, and we do not put anything yet. The jury is still out. After the tasting number 2, the horizontal mouse survives. What does it mean 2? 2 goes into here. So let's say we put 2. The name of the poison bottle is 20. It's this one. Evidently, again, because I messed things up over here so that you guys can see the geometry, after the vertical mouse died after the first test, it means that the poison bottle is one of these two. We gave to the mouse MH, to the horizontal mouse, we gave the wine from which bottle? From this bottle, exactly. One had to be in the leftmost position of the tertiary name of that bottle that went into the cocktail named H. And amazingly enough, lo and behold, the horizontal mouse lived. No poison here, poison over here. What does our algorithm mean? 2O, 2O exactly is where the poison is. Let's say horizontal mouse was not lucky at the end of the second test. We go back to our table, we inject 1. So now over here in this case, instead of 2, let me erase 2. Where is my green? So with the green we write 1. 10 is the name of the poison bottle. Why is that? Well, again, from that bottle we gave precisely that bottle was one of the bottles, the wine from which went into the mix that was given to the horizontal mouse. The mouse passed away. Evidently, the poison bottle is this specific one, and you can play with these different scenarios. Just make sure that you come up with the realistic scenarios. You cannot just blindly mix the results. You have to mix the results in such a way that it is possible, so that overall the test that we designed, the tasting 1 and tasting 2, makes sense, and your results are possible on the assumption that there is only one, not 2 or 3, but there is only one poison bottle. Now that we understand how a geometric and how an algebraic solution of the 9 bottle problem works, we will refresh in our memory fairly quickly, because we did it already in the past, the equivalent geometric and algebraic solution of the 9 coin problem. With the 9-coin problem, the objective is to find in no more than 2 weighings with absolute certainty the identity of the fake and heavy coin, given a properly functioning, not rusty or anything, a properly functioning set of pen scales, and 9 visually indistinguishable coins. I will not be going into the detailed solution of the 9-coin problem as I just did for the 9-bottle problem, because for those of our viewers who joined our channel later, we suggest that you guys find the episode named Season 2 Episode 14, shown over here, Season 2 Episode 14. The link to the season guide is in the comment section. You can click on that link, go to my GitHub repo, view or download the free PDF file. In that PDF file, zoom in on this episode and click on the link. It will take you exactly to the episode which we covered, or maybe you are way better at searching for the episodes on this platform than I am. If you can find by other means, this is the guide to find, Season 2, Episode 14. The name of the problem was S2M16. That was the problem in mathematics number 16. So either way you can find this material. We explained in great detail how these geometric solutions in fake coin problems work. As a matter of fact, the title of Season 2, Episode 14 was precisely that, Geometry in Fake Coin Problems. And A geometric solution of the 9-coin problem is tantalizingly close to the geometric solution of the 9-bottle problem that we just discussed, but upon closer inspection, it turns out that it is not really that close. But the idea here is the following. Arrange the 9 visually indistinguishable coins as I showed over here in yellow circle. Hopefully you guys can see it. Let me make it a little brighter. As a 3 by 3 square, again, just like we did with the bottles. 3 by 3 square, yes. And then pick any 2 parallel straight lines that must be distinct and that pass through the 3 coins. For example, this blue line and this blue line, the choice is arbitrary. You can pick this one and this one. It doesn't really matter the way the geometry of the 9-coin problem works. That's how it goes. Any 2 straight lines that are parallel and that pass through 3 coins. Arbitrarily, again, decide which line will represent which pen, left or right. Here, for demonstration purposes, I put the right one, the top blue line represents the right pen, and the bottom blue line here represents the left pen on the pen scales. Once the choice is made, mechanically roll through the coins through which your straight lines pass and ink the name or the letter which corresponds to the pen. L, L, L in the first position, R, R, R in the first position, right pen, left pen. Perform the weighing, record the result blindly again. This is not an adaptive solution, it's mechanical, and that is why that is the solution types for fake coin problems that we discussed. That's why I named the corresponding episode Blind Mathematical Justice, because here we carry out steps mechanically, blindly, meaning not optically but intellectually. Name things, put coins, record the result. If the right pen went down, we record the name R, for example, on paper. If the left pen went down, we record L, or we mark which straight line corresponded to the pen that went down. Remember, the fake coin is heavy. It is known that it's heavy. With the light coin is the same thing. If neither pen went down, this is the straight line that corresponds to our solution. This one, the B, 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 the balanced one. Then for another, this is for the weighing number 1. For the weighing number 2, you represent the weighing number 2 with a different set of parallel straight lines which intersect the original pair of straight lines. So here the second weighing represented by these 2 red straight lines shown over here. Again, absolutely arbitrarily decide which straight line will represent which pen. Here I purposefully switch things around. This straight line represents the left pen. This straight line represents the right pen. Again, mechanically roll through the corresponding coins that sit on these 2 straight lines and write down your choice. R, R, R for the right pen, L, L, L for the left pen. Game over. Perform the result, perform the weighing, observe the result, see which pen went down, note the straight line that corresponds to it. Bam, the intersection of 2 straight lines that are the result of 2 weighings marks the spot, identifies the fake and heavy coin. For example, let's say during the first experiment, the left pen went down. So we keep a note of this straight line over here. This is the guy, went down. And when we perform the second test, we realize that this pen, the left pen, went down. So this corresponds to this straight line right here, this straight line as I wrote over here. What does it mean? It means that the coin that is fake and heavy, the identity of the coin is recovered with absolute certainty as what? As an intersection, or as the intersection of the straight line that were the result of this experiment, 2 weighings, and bam, it's circled over here. This is the identity of the coin that is fake and heavy. Let's say in the first experiment no pen went down, but in the second experiment still this pen went down. Well, the balanced straight line intersected with the red one names the spot. Let's say no pens went down in this test, no pens went down in this test. Then what? Well, 2 balanced lines, this one and this one. This is the name of the fake and heavy coin. So this is it for the geometric solution of the 9-coin problem. Again, if you joined our channel later in season, we recommend that you guys find this episode and work your way through it, because you need to be in a very firm and solid command of how the solution of this 9-coin problem works and unfolds, because we're right now studying the our less, so to speak, official problem solving approach. It is quite complicated. It requires an extra ability for the, or an extra power of abstract cognition. We will be comparing the two solutions to the two problems that we just solved, and we will be making certain conclusions. So it is in your personal, for your, in your personal interest to be in a good command and understand well how does a geometric solution of the 9-coin problem works, and how does an algebraic solution of the 9-coin problem works. And again, we will briefly discuss it in the next segment. An algebraic solution of the fake coin problems we discussed in season 2, episode 15. That was our mathematical problem S2M13. So for those of our viewers who joined our channel later in time and missed that episode, it is a good idea to go find that episode and watch it and work their way through again. S2E15, Season 2, Episode 15, in which we discuss at length the solution of the mathematical problem S2M13. And do not worry, I managed to find all the links to all the relevant episodes in the comments section. Please check the links. You will find the link to the episode, Season 2, Episode 14, which discusses a geometric solution of the 9-coin problem S2M16. You will find in the comment section the link to the episode S2E15, where we discuss at length an algebraic solution of the fake coin problems. This was the problem S2M13. And again, if you missed those episodes, we suggest that you work your way through it, because I will explain why in a few seconds. So here, the algebraic solution of the 9-coin problem is very similar again, but subtly and fundamentally different from the algebraic solution of the 9-coin problem. What do we do here? For an algebraic solution of a 9-coin problem, we arrange the 9 coins, again as shown with yellow dots, into a 3x3 square formation. And again, we assign 2-bit unique tertiary names to these coins in any which way. I use the tertiary alphabet of the letters L, shown in red, R, shown in green, and B, shown in blue. And for example, I decided to name the top row of the coins as L, 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 L. The middle row I named with R, 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 and the bottom row I named with B, 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 B. In the second position, I record the column number, so L for the first L, L shown in red, R for the second position, for the second column, R, 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 and B for the third one, B, B, B. Consequently, we generate all 9 finite linear permutations, 2 bits wide, of 3 distinct symbols that make up the alphabet of the base 3 or tertiary numbers. And now what do we do here? We do the following. For the test number 1, that's designated over here on top, 1, 1, 1, and 1, 1, 1, we only work with the first or leftmost bit of each and every tertiary name of the coin, unlike the way in which we worked with the 9-bottle problem. Here on the left pen, we put all the coins that have the letter L in the first bit of their tertiary name. And these coins are what? These coins are named L, 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 R, and LB, precisely because L is in the very first or leftmost bit in their 2-bit unique tertiary names. Onto the right pen, we put all the coins that have the letter R in their first. Again, it's important to realize here, first, we're not switching gears like we did with the 9-bottle problem. We're still staying for the weighing number 1, we're staying with the position number 1. with the leftmost position, which must carry the letter R in the 2-bit unique tertiary name of these coins, and these coins go onto the right pan for weighing number 1, RL, RR, RB. Here we perform the weighing, we record the result blindly, mechanically. Let's say the left pen went down, so we record the letter L into the first position. For the weighing number 2, we do the same thing, but now we work with the second position, with the rightmost bit in the name of each and every coin that was assigned a unique 2-bit tertiary name. And onto the left pan, we put all the coins that have the letter L in the second or in the rightmost bit of their unique tertiary name. As shown by me over here, I put the number 2 for you guys, 2, 2, 2. So all the coins that are named L, L, R, L, and BL go onto the left pan for the weighing number 2. Onto the right pan, you probably already guessed by now, I figured it out, that onto the right pan there go all the coins that have the letter R. Right pan, letter R in the second or rightmost bit position of the unique 2-bit tertiary name. R, weighing number 2, R weighing number 2, R weighing number 2. And you can see, again, with this approach, the algebra and geometry again enjoy a wonderful and fruitful relationship. You can see the letters L for one pan and letters R for the other pan. These are our two parallel straight lines in one way. The other way, we go vertically, for example, here, L, 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 R, R, R. So all the coins that are named L, R, 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 and BR go onto the right pan for the weighing number 2. Perform the weighing number 2, record the result mechanically. Let's say no pans went down, the pans balance. We write down B into the second position. LB is the name, is the identity of the fake and heavy coin, determined with absolute certainty. Where is that coin? That coin is right here. Turned out that is the fake and heavy coin. But depending on the result, again, the result of the first experiment is written into the leftmost position, and the result of the second weighing is written into the rightmost position. This is also non-negotiable, blind mathematical justice, non-adaptive algorithm. The way things happen, we write them down, mechanically announce the result at the end of the measurement. And again, you can see how it is possible to, for example, correlate one solution to another. If you invented a geometric solution of the 9-coin problem first, well, you eventually should converge onto an algebraic solution that is similar to this one. And conversely, if you discovered or invented an algebraic solution of the 9-coin problem first, then it is transparent to see the parallel intersecting straight lines and concoct the geometric flavor of the solution of the 9-coin problem. Now, why I stress the fact that if you guys are watching this episode, then you're in for hard work, is because the problem-solving approach that we're studying right now is the more or less the final approach in my sequence of studying the problem-solving approaches, is the most difficult one. The approach of mathematical equivalence requires a reasonable amount of mathematical maturity, mathematical experience, and the powers of abstract cognition. And that is why it is in your best interest to be in firm command of the mechanics of how the solutions of these two problems work, and both flavors of these solutions, the algebraic and the geometric solution. Now, why is the problem-solving approach, to which I refer as mathematical equivalence, is so difficult? Well, we've spent pretty much the entire season, that's 52 weeks and almost 50 odd episodes, fighting the fight with generating one solution for one problem. In other words, climbing the mountain of generating one solution is a challenge enough. But now we take this for granted. We assume automatically that you, I, we collectively can solve these two problems. And now what we want to do, we want to step up in our intellectual effort and in our ability of abstract cognition and compare. See, this is what we're doing right now. Compare the solutions of two seemingly difficult technical problems. So how do we compare solutions? We compare solutions of technical problems by comparing the structure of these solutions. And what does it mean to compare a structure? What is a structure of a solution of a mathematical problem? Or what is a structure of a problem in, for example, of a solution of a problem in theoretical physics? Well, this is a delicate discussion. It's The structure of a solution of a mathematical problem is a fairly abstract idea or fairly abstract notion because it can be represented with different mathematical objects. For example, with a graph, which is an object of study of the theory of graphs, or with an equation. It could be a differential equation, an algebraic equation, or a trigonometric equation. As such, right now, and I will say a few words about this in the next couple episodes, right now we want to inhale both types of solutions of the problem 1 and problem 2 and compare them. Can a solution of one problem be converted into a solution of another problem mechanically? If we suspect that the structures of the solutions of two technical problems are one and the same, or virtually indistinguishable, or isomorphic in a sense, then the first order of business in an attempt to map a solution of one problem into a solution of another problem is to map the local material across the two problems. That mapping process is an art and a science, but I think that that process is more of a science because usually it's quite evident which local material in one problem goes into the local material in the other problem. In mathematics, for example, we have a precise notion of a bijection or of a bijective mapping. That is, a mapping is bijective if and only if it is both surjective and injective. A mapping is injective if it is one-to-one, and the mapping is surjective if it covers the entire destination set. In this particular case of mapping the local material from one problem to another, I do not think that we can bring in this exact and precise notion of bijection, but we can think of it as a vague bijection. So how does this vague bijection across the material of two problems work? Well, in our case, we have a 9-bottle problem and a 9-coin problem. So here in yellow on the top, I try to capture that mapping of the local material of one problem into the local material of the other problem. And again, like I said, that process is both an art and a science, but I think there is more science in it than art. Why is that? Well, let's take a look. In the 9-bottle problem, we have 9 bottles, and the whole battle is revolving around the identity of the poison bottle. And in the 9-coin problem, we have 9 coins, visually indistinguishable, visually indistinguishable. So what's going on over here? Well, it's natural to map a bottle to a coin and a coin to a bottle. Thus, this mapping is shown over here. A bottle corresponds to a coin and a coin corresponds to a bottle. Now, the next step, we keep mapping the local material. What's going on with the bottle in the 9-bottle problem? Well, the bottle may contain a poisoned wine. And what's going on with the coin in the 9-coin problem? Well, coin may be fake. Thus, the next mapping that we establish is between the notion of poisoned wine and the quality of the fake coin. So the fakeness corresponds to poison, poison corresponds to fakeness, or to the weight quality of a not fair coin. What is the next mapping of the local material? How do we identify the bottle that is poisoned? Well, we perform a tasting. And how do we identify the fake coin? We perform a weighing. Thus, it is natural to map, or again, vaguely, let's say, biject, a tasting to a weighing and a weighing to a tasting. Very good. Now, the last piece that we need to deal with in this mapping is what? Well, what do we put the coins on? Depends in the 9-coin problem. And where do we put the wine in the 9-bottle problem? Well, technically we put them into a mouse or into mice, let's say. So thus we establish the following mapping: mice to pens, pens to mice. In other words, one mice corresponds to one pen and one pen corresponds to one mouse. And that is the mapping. This is how the mapping of the local material work. Once that mapping is established, now we try to basically take any one solution of any one problem and mechanically map or translate it into a solution of the other problem. And again, here for some of our viewers, the notion of mechanical transformation may be a little bit vague and not clear, and admittedly there is some vagueness in that notion, but the idea here is to create this mapping of one solution into another with minimal effort. This is what mechanical transformation, that's what it means. No clever transformations, no clever combinations of things, pretty much mechanical, almost no thought involved process of saying this is what this is in one problem, and given this solution and this mapping, bam, this is what it must be in another problem. So for example, let's talk about the geometric solution or geometrically flavored solutions of our two problems. If we try to map a geometric solution of the 9-bottle problem into a geometric solution of the 9-coin problem, mechanically, what will we have to do? Well, we remember that tastings correspond to weighings. So here we will have to do what? For the first tasting, we take the mix of cocktails from bottles that intersect at precisely one bottle. So if we were to translate this into the whole arrangement of the process into the context of the 9-coin problem, geometrically still, what will we have to do? Well, what does it mean to share the wine from one bottle across two cocktails that are given to two mice? In some sense, we have to violate the physical integrity of one coin. We have to split it somehow. If we split it into two different masses, then it doesn't make any sense. If we put differently sized or different amounts of mass on a balanced pen, the pens will not balance. This will introduce the difference. It will complicate the matters more than we have to. If we split the coin exactly in half, then whether that coin is fake or fair, it doesn't really matter. The two halves will have the same mass. And if we put exactly two same masses onto balanced pens, this will not introduce any difference. The pens will still remain balanced. And the whole idea in the 9-coin problems is to exactly introduce the difference by shuffling coins from one pen to another to introduce the difference that can detect the single fake coin. So this mapping over here, the mechanical mapping of a geometric solution of a 9-bottle problem into a geometric solution of the 9-coin problem, evidently does not work already. Conversely, let us try to convert the geometric solution of the 9-coin problem into geometric solution of the 9-bottle problem mechanically. What does that mean? Well, that means that we will feed the cocktails to two mice. We'll create two cocktails, and then we will feed them to two mice based on the parallel lines idea. In other words, for the cocktail number 1, we will take the wines from, let's say, top horizontal bottles, and this cocktail will go into the, let's say, mouse M H, and doesn't matter for the second cocktail. For the tasting number 1, again, for the tasting number 1, we will mix the wine taken from the 3 bottles that sit below. This cocktail will go to the mice MV. We will still have 3 bottles over here. And well, how can this testing scheme even work? Well, if neither mouse dies in this case, yes, it can work, because now we eliminated 6 bottles from suspicion, 3 bottles are under suspicion, and we have what? 1 tasting left, 2 surviving mice, And how many outcomes does this experiment produce? Well, it can produce no more than 3 outcomes. Both mice survive, this mouse dies, or this mouse dies. So this is precisely 3 outcomes. And these 3 outcomes of produced information can be mapped uniquely to the 3 units of existing information. For example, we give the cocktail from this bottle to one mice, MH. We give the cocktail from this bottle to the mouse, MV. No cocktail, no wine is taken from this bottle. If both mice survive, this is the poison bottle. If this mouse dies, this is the poison bottle. If this mouse dies, this is poison bottle. Very well. But what happens if one, as a result of the first tasting described over here, one mouse dies? Well, we now have 3 bottles under suspicion with absolute certainty. We have 1 surviving mouse left and 1 tasting. With 1 tasting and 1 mouse, how many units of information can we produce? No more than 2. This mouse either dies, that's 1 outcome, or it does not die, 2 outcomes. And these 2 outcomes must be mapped to 3 units of information over here in a distinct way. Can this be done? No, this cannot be done, precisely because 2 is less than 3. So now we see that in either direction we have problems that we cannot reconcile mechanically, and that means that no geometric solution of either problem can be converted into geometric solution of another problem. Now let us take a look at what is going on with the algebra of the solutions to these 2 problems. Those of our viewers who are sufficiently convinced that separately an algebraic solution of one problem is equivalent to a geometric solution of the same problem may already be also convinced that if we show that geometrically the solution of one problem cannot be converted into a geometric solution of another problem mechanically, that failure means that the same failure awaits us in the land of algebraic solutions. But if you're not sufficiently convinced, let us do that explicitly. In other words, if we are to try to map an algebraic solution of one problem into an algebraic solution of another problem mechanically, we will not be able to do that because, let's say, in the 9-bottle problem for the tasting number 1, we use one and the same tertiary symbol that is put into 2 different positions. And here we pay attention. In the 9-coin problem, we actually do go the other way around. We put different tertiary symbols into one and the same position. So in some sense, the roles of positions, the bit positions in the 2-bit tertiary names of the objects in each problem is swapped with the alphabet that we use, the tertiary symbol alphabet. And let's say we try to explicitly map an algebraic solution of a 9-bottle problem into an algebraic solution of the 9-coin problem. That means that, again, if we are to do that mechanically, we have to put for the test number 1, or for the weighing number 1 for the 9-coin problem, we will have to put what? All the coins that have the symbol L or 0 in the first position of their 2-bit unique tertiary name onto the left pen. But then look at this. The algebraic solution of the 9-bottle problem prescribes that we reuse the same symbol, the same tertiary symbol, for the mixing of the cocktail for number 2. Here that means that if we correlate a mouse to a pen, if the cocktail number 2 that goes to a mouse number 2 is associated with the position number 2, here that means in the 9-coin problem that we still have to take all the coins that have the symbol, the tertiary symbol L, or the tertiary symbol 0 in the second position of their unique 2-bit tertiary name and put them where? Onto the right pen. This is the only option. But this is precisely the problem, because in the 9-coin problems, we work for each specific test, for each specific weighing, with a fixed position. In other words, for the test number n, if there is a test that is numbered with n, we have to work with the bit position number n. So bit position also must be n, and these two numbers must be in sync. Bit position corresponds to the test number and test number to the bit position. And here we're asked to violate that idea and look for the specific letter in the second position of the tertiary name of each coin, which we assigned as we explained. So that is a problem that cannot be reconciled mechanically, because bit positions is a big deal. They're very sensitive and they're very important. They cannot be played with willy-nilly. They are fixed and carry their own great weight when it comes to expressing the local material in the specific base 3, for example, in this case. Conversely, let us try to mechanically convert an algebraic solution of the 9-coin problem into an algebraic solution of the 9-bottle problem. What will happen then? Well, for the tasting number 1, we will have to do what? For the first cocktail, we will have to take all the bottles that have the tertiary symbol L or 0 in the first bit position of their 2-bit unique tertiary name, which is fine. This is what we wanted to do. This is what we wanted to do in the original solution. That is fine. That looks promising. But look then, what happens then? For the cocktail number 2 that we feed to the second mouse, we have to take all the coins that have the symbol R, or in our nomenclature it was symbol 1. Symbol 1 again still in the first bit position of the unique 2-bit tertiary name. This is precisely the violation of the idea. In our original solution, we still used the same symbol, but we looked for the symbol 0 in the second bit of the unique tertiary name. Here we need to look for all the bottles that have the symbol 1 in the first position, in the first bit of the 2-bit unique tertiary name. And what does that mean? Well, that means that we will have to sample precisely for the second cocktail, we'll have to take the wine from the bottles that sit in the second row. 1 something, 1 something, 1 something. And this precisely already, we analyze this case, we know that this cannot work. So the mapping over the algebraic solution of the 9-coin problem into the algebraic solution of the 9-bottle problem also cannot work. These problems cannot be reconciled, and that means that mechanically we cannot convert the algebraic solution of one problem into the algebraic of another problem. And the reason I wanted to bring these two problems to your attention, again, my claim that the conversion of one solution into a solution of another problem cannot be done under this mapping. Maybe someone in our audience can create a different mapping over here, and under that mapping, maybe in some clever way, you can map a geometric solution of one problem into another, or an algebraic solution into another. If you guys can do it, let me know. I'm curious to see how this can be done, but under this mapping, I just showed that this cannot be done. And the whole idea of this exercise is the following. Across the two problems that we solved in this episode, the 9-bottle problem and the 9-coin problem, we saw how two problems that are worded differently bottles, poison. One is very different from coins, pens, and weighings. The solutions of such two problems can be brought tantalizingly close to each other, but such solution fails to be identical or virtually indistinguishable from each other. And it so happens that across mathematics, theoretical physics, computer science, and perhaps some other technically related areas with which I'm not that familiar with, it can so happen that two very differently worded problems can have the solutions whose structure is identical or virtually indistinguishable or isomorphic. So for some of our viewers, the question on their minds right now, what is a structure of a solution of a mathematical problem? Well, that notion is somewhat abstract because that notion can be captured with different objects, but I think that the main idea here is to represent or somehow boil down the sequence or the chain of steps that is a solution of a mathematical problem to a small number of objects that can be compared in a meaningful way. For example, let us say we take a technical problem, which could be a problem in mathematics, electrical engineering, or computer science, or whatever, and we reduce the solution of that problem to a graph, which is the object of study of the theory of graphs, and one such graph is shown on the left side of your screen over here. Such graph, as we all know, is the animal that's made basically of two things: a set of the so-called vertices or nodes and a set of edges. The edges could be directed or not and so on, but that doesn't matter for us. For us, what matters is the following. Let's say we took one problem, reduced its solution to a graph. This is the graph. Wonderful. We come across a different problem that may be from a different technical area, worded totally differently, but magically, lo and behold, we reduce the solution of that second problem also to a graph. And oh my God, look at this. The graph in the second problem is isomorphic to the graph in the first problem. If we recall the strings and billiard balls model of a graph, we know that we can continuously transform this set of strings and billiard balls in a contiguous way without ripping any strings that connect the billiard boards, and voila, we have two isomorphic copies of one and the same graph, which is basically this is what it means to say that these two graphs are isomorphic or identical in structure, and that the identicalness of the structure of the underlying graphs translates into the identicalness of the structure of the solutions of these two problems. Now, what is the next low-hanging fruit? Well, aside from a mathematical graph, which is the object of study of the theory of graphs, the next low-hanging fruit is an equation. Equation comes in different flavors: algebraic, trigonometric, differential. Differential equations is their own universe, but here this precisely what it is. If we can take two wildly different problems, one from mathematics, one from physics, or whatever else, and reduce it to an equation, let's say differential equation, that looks exactly the same way, if we rename the variables accordingly, then voila, we know that the structure of the solutions of these two problems is identical. This is precisely what we will do across the two episodes, season 2 episode 53 and season 2 episode 54. We will solve two wildly different problems, that both of which can be reduced to one and the same ordinary differential equation of order 2 that has the following shape, provided, of course, that we rename the local variables accordingly. Here I stole the letter Q as a generalized coordinate from theoretical physics, but the idea here is the following. In season 2, episode 53, we will deduce the so-called Lanchester's square law. We will solve a problem that deals with certain processes that unfold between two fighting armies. And in season 2, episode 54, we will solve a problem where we will have a bead sliding over a needle that rotates around one of its extremities in the horizontal plane with a constant angular velocity. And once we solve that problem, we will realize with the solution of the problem here in season 2, episode 53, that both of these problems mathematically are reduced to one and the same ordinary differential equation of order 2. And this is actually one thing that is absolutely amazing, because how can two fighting armies, for example, the old style ships of the line taking salvos at each other, be any same as a bead sliding without a friction over a needle that rotates in the horizontal plane with a constant angular velocity? The language of beads, needles, rotations with constant angular velocity in the horizontal plane is wildly different from the two armies made up, each of which is made up of, let's say, ships of the line taking salvos or firing cannons at each other. How can this be any more different? It is wildly different. Meanwhile, underneath all that difference, there sits one and the same differential equation, ordinary differential equation of order 2, and according to the corresponding theorems that are the bread and butter of the theory of differential equations, the theorems that deal with existence and uniqueness, we know that the solution of such an equation exists and it is unique. Because it is unique, that uniqueness gives us the right to say that the structure of the solutions, the mathematical structure of the solutions of these two wildly different problems is one and the same. Now, we will solve the problem with the Lanchester's law, Lanchester square law in season 2, episode 53, in all of its excruciating details separately in isolation, pretending that this problem doesn't know that the other problem even exists. We will not spare any details. We will um, leave no stone unturned. We'll take all the zigs and zags, twists and turns in each problem separately, and we will produce the solutions of them independently. And then in season 2, episode 55, we will show precisely how to, let's say, take the solution of the fighting armies problem and flip it mechanically into the answer that we will be looking for in season 2, episode 54. Now, as a heads up, the name of the episode, season 2, episode 53, will be Lanchester square law. The name of season 2, episode 54 will be slitating or roll-lighting bead, precisely because this bead participates in two motions, but we will get to it in due time. And the title of the season 2, episode 55 will be mathematical equivalence, and we will see how does the method of mathematical equivalence work. And all this material is very exciting and interesting and has a fair amount of depth to it, precisely because it will help us understand better what mathematics is. Recall that in season 1, episode 1, I opened the life of this channel with a discussion of what mathematics is, because this is very important. And looking through this material will precisely help us understand what mathematics is. This is, again, very exciting, very interesting. It has a good amount of mathematical heft attached to it. And we will witness firsthand. It is important to witness all these ideas firsthand. We will not be reading about this in some book. We will walk the walk every millimeter of the way from A to B, and then we will able to see and comprehend the power of mathematics. Because look, here we take some material, and in this problem we also take some material. We shake these two problems, but we shake them down in such a way that the secret sauce that sits inside these two problems, boom, produces one and the same thing. One and the same thing happens to be an ordinary differential equation of order 2 that is one and the same. And that secret sauce is mathematics. That's exactly how these things work. And this is the essence of the method of mathematical equivalence. Now, a few words for the more mathematically mature audience. This idea, you may discern, also unfolds in the theory of groups all day long, where we can have two different groups that are worded very differently, but these groups structurally are the same, or these two groups have two identical structures. To give a baby simple example, let's say the we take the non-square rectangle, congruence motions of the non-square rectangle under the operation of composition. This pair will produce a group that is isomorphic to the Klein 4 group. And on the other side over here, this is all sorts of material, many different things. But let's say, to be wildly different for computer science oriented audience, let's take the binary strings of length 2, 0, 0, 0, 1, 1, 0, and 1, 1 under the operation XOR. Under the operation XOR. How different these two materials can be. Congruence motions of a non-square rectangle, binary strings of length 2. How are they related? There is no relation. Composition in one case, XOR, binary XOR in the other. How are they related? There is no relations. Yet, it is the case, and it is shown in the theory of groups, that structurally these two groups are indistinguishable, virtually the same, or isomorphic. And what does that mean? Well, the structure of a group is a specific way in which the elements of a given group interact with each other under the group operation. And the fact that the two groups are isomorphic means precisely that, regarding or despite the fact that the material is across two groups is different and the operations across two groups are different, the way in which the local material in each group interacts with each other under the group operation is one and the same, virtually is indistinguishable or isomorphic. Again, this will be very exciting, very interesting, very deep, and it will be difficult. It will not be easy, but I will do my best to keep the mathematics across these 3 episodes to a minimum. And this is it for the mathematical problem S2E52. And we will move on to the new challenge over here, the Lanchester square law, next. Now that we know the program that lies ahead, let us get to it. In the next challenge, which will be the mathematical problem S2M53, we have the following setup. We have two fighting armies, or two armies that are about to enter into a battle. The Army A and the Army B. Initially, before the battle, the Army A has A0 fighting units, soldiers or ships of the line, for example, and the Army B has B0 fighting units. And for definitiveness, let us say that there are more fighting units in the Army A than there are in the Army B, and this inequality is strictly larger than. Then we're also given that we have two numbers, each of which can be called, for example, lethal skill. And what is a lethal skill? A lethal skill is the number of fighting units of the opposing army. One fighting unit of the original army can take out of the fight, out of rotation, so to speak, per unit of time. Per unit of time. Per unit of time. For example, alpha, let's say we agree alpha is the lethal skill possessed by each and every fighting unit of the Army A, which is the number of fighting units of the Army B, because this is the opposing army. One fighting unit of the Army A can take out of rotation, out of the fight, out of the battle per unit of time. And likewise, beta is the number of units of the Army A, because for the Army B, the Army A is the opponent. One fighting unit of the Army B can take out of the fight, out of the battle per the same unit of time. These numbers are constant, 0.8, 0.7, or some such. It doesn't really matter. We hide all these specific numbers behind these two symbols. Constant numbers. We're also given a bunch of constraints, or we already know. We dealt with differential equations before. We know that all these assumptions is the set that makes up a mathematical model of whatever real-life phenomenon we study, and these assumptions are just here for you guys to deduce the corresponding differential equations. There are actually way more assumptions than this. Once you begin digging deeper into all this mathematics goes to war business, you will discover that this is just toy assumptions. There are way more, and different assumptions produce different models command different mathematics, and so on and on and on. We don't want to deal with that, but for the sake of you being able to deduce the corresponding differential equations, we take it that the attrition in this model is linear, the time model is continuous, both armies have an infinite supply of ammunition. There is no problem for them to reload their fighting tools and fire off the next shot. And we're also no replenishment of fighting units. So, for example, in our lethal skill alpha beta, whether the fighting unit is, what does it mean to be taken out of rotation or taken out of battle? Maybe it's completely killed, maybe it's wounded, maybe it's partially destroyed, maybe it's still on the battlefield, but it does not present any danger, even though it's not completely destroyed, and so on. We hide all this, taken out of rotation, taken out of the fight, and that unit will not present the danger to the opposing army anymore. So no fighting unit replenishment. Once the unit is taken out of rotation, taken out of the battle, that's it. New similar fighting units are not delivered into the battlefield. This is sort of closed combat model, meaning that the initial numbers that go into the battle, A0 and B0, this is it. This is what both armies have, and no resupply, no replenishment is coming. So here, under these conditions, we have, and again, this is just a small number of initial assumptions that create the mathematical model, the axioms of this model, if you will, but there are more over here, and you will discover them as you go. I just wanted to list this four so you can get going. So we have two questions in this problem. The number of survivors, let's say it so happens that the lethal skill and the number of the initial number of the fighting units between the armies A and B is balanced in such a way that, yes, it so happens that Army A wins, for example. And again, this is a mathematical model. This is not the real thing. We want to study the situation when the Army B is completely annihilated, and at that time when there are no more fighting units of the Army B left, how many fighting units of the Army A will there be? So the first question is the number of survivors when the opponent is completely annihilated. Question number two is the annihilation time. How long will it take the Army A to completely destroy and wipe out the Army B? What is the time when no more fighting units of the opposing army left standing? Again, as you can see right away, there is another hidden assumption that I did not write. Like I said, there are more assumptions over here. Even though, let's say, during the battle, the fighting units of the Army B realize, oh, this is it. I mean, we're getting destroyed completely. We're getting annihilated. Knowing that the fighting units of the Army B still, of the losing Army B, still decide to fight to the bitter end, even though they know that they're about to be wiped out completely. So whether, again, how realistic that is, will they fighting units of the Army B run away, surrender, or whatever, it's completely irrelevant for our model. This is the assumption that even though the fighting units of the Army B do know that they're about to be completely wiped out and destroyed, they still continue to fight, business as usual, so to speak. Under these conditions, we have these two questions. The number of survivors of the winning army under the condition that the opposing army is completely wiped out, and the annihilation time. How long did it take the Army A to completely annihilate the Army B? And the definition of complete annihilation: no more fighting units of the Army B, of the opposing army, left standing. This is not an easy problem. This will be difficult. Try to do your best. Even if you make partial progress, that is good. But what we're looking for in this problem is not just the construction of the corresponding differential equations. At the beginning of the next episode, we will do so in about 15 seconds or less. What we're looking for is a solution of the resultant differential equation in all their gory details. You're expected to produce step-by-step example or step-by-step sequence of steps that take the given differential equations, given initial conditions, and boil down all the way to the actual solution. So here we want eventually, we want A of t and B of t, the number of fighting units of the Army A and the number of uh, fighting units of the Army B as a function of time, explicit function of time. This is a miracle. This virtually never happens. All the differential equations that are realistic are not solvable analytically. This time it is possible. I'm giving you a heads up. A finite combination of elementary functions sits behind these two functions, A of t and B of t. Find these guys, produce them, and show that deduction process step by step, not omitting a single detail. This is it for this episode. Thank you very much for your time. Thank you for watching. In the next episode, I will show my solution of the mathematical problem S2E52.